Hello, class. This is Professor Kamen, and this is your manufacturing processes. That's machining 1319 video presentation for the manufacturing process of machining. Now, machining is a fairly old manufacturing process and is very common nowadays. And you actually might be a part of the machining program here at Lone Star College. And so I'm sure you are familiar with what we're going to be talking about today, but there might be some things that you have not heard about, some things that you might not be familiar about. And for those who are not familiar with the machining process, well, that's what we're here for. So let's go ahead and get started with our presentation. So let's ask ourselves a question, what is machining? What I'm going to do is I'm going to move myself up here a little bit and then minimize this so I'm not in the way. There we go. Okay, so hopefully this will work out a little bit better. How about I move down here? Yeah, that'll be better. So what is the machining process? Well, machining is really a very general term. It describes lots of different individual processes that really focus on removing material from a workpiece. Now, this can be done with lots of different materials. This can be done in lots of different, very specific ways. And we're going to talk about some of the most common ways, but that's the basic definition of the machining process. What you're doing is you're removing material and then at the end is going to be your final workpiece. So what about the machining pros and cons? For each manufacturing process that we're talking about, you're going to have some advantages and some disadvantages of that process. In particular, for machining, precision is one of its greatest advantages. Not many other technologies, not many other manufacturing processes have the precision that the machining process has. It can produce parts with tolerances up to 10 thousandths of an inch. So normally, 1 thousandth of an inch will do. Now, because of that and related to that, it can also produce a very, very high, very, very clean and smooth and shiny surface finish, which is also a very good quality. So these qualities are both higher than any other manufacturing processes that we've talked about, including casting, including hot working, cold working, powder metallurgy, okay, and lots of other processes that we've yet to talk about as well. Now, what are the cons? What are the disadvantages of the machining process? And the main disadvantage is that machining is very, very expensive. The reason why it's so expensive is because it's a removal process. That means you start off with a lot of material and then you remove some material until you are left with your design, with your final part. So what do you do with all that material that you've removed? Well, sometimes you can recycle it, but then sometimes you can't recycle it. And so that material is just gone, it's wasted, it's not used. And so that's why the machining process is a very, very costly process. That's its main disadvantage. Now let's look at some of the common individual manufacturing processes within machining. And this first one is a video on milling.
Milling edges, shoulders, and grooves may use a combination of end, peripheral, and/or face milling operations. Creating edges or edging may involve the milling of one or two surfaces. Shoulders typically have two surfaces, and grooves usually have three surfaces. Grooves may be closed at one end or open at both ends, and they may be cut on internal and external flat surfaces as well as on round surfaces. Peripheral milling cutters have cutting edges on their periphery, which are parallel with the axis of rotation. Peripheral milling is useful for creating long open slots and forms. End milling cutters are round shank tools with cutting edges on their periphery and end. The axis of rotation is perpendicular to the surface produced by the end of the tool. Cutter size is defined by its diameter and cutting depth. Since end mills cut more with the teeth on their periphery than with the teeth at their end, they are susceptible to lateral forces. This makes them subject to deflection, which reduces the accuracy of the milling operation. Short, shallow slots are often created with end mills. Deep, narrow slots may be milled with an end mill, a thin slitting cutter, or a grooving cutter. Grooving or slotting cutters are generally more efficient than end mills for cutting long and deep slots because of their larger diameter and greater number of teeth.
All right, now let's talk about another process, which is the drilling process.
The key operating parameters in drilling include cutting speed and feed or penetration rate. Drilling conditions influence these parameter selections. Cutting speed for drilling is measured at the periphery of the drill and is expressed as surface distance per minute. It varies from a maximum at the periphery of the drill to zero at its center axis. As a rule, the harder the material being drilled, the slower the speed used. The feed or penetration rate is a distance per unit time and is expressed in inches or millimeters per revolution of the drill, or in inches or millimeters per minute. Generally, the feed rate must be reduced, sometimes up to 50%, when drilling into curved or sloping surfaces, drilling across another drilled hole, or when enlarging a pre-drilled hole. Excessive feed rates can cause chipping or fracture of the cutting lips, as well as splitting of the drill's web.
So that was a video on the machining process of drilling. Here's one on the machining process of turning.
There's a wide range of cutting techniques that can be done in a smithy. All of them, no matter how complex, can be done efficiently, as long as you follow a few simple guidelines. The first and most important thing to remember is that the cutting tools, the drills, lathe tool bits, and milling cutters must be sharp. Second, cutting tools must be held securely in the machine's tool holders, free from any vibration. Third, the workpiece, or in other words, the metal you intend to cut, must be mounted securely on the machine, able to resist the force of the cutting tools. And fourth, the correct cutting speed should be used. These 4 points, tool sharpness, tool holding, work holding, and speed of the cut, all have a direct effect on the ability of the machine to work efficiently, and in the long run, an effect on the quality of your work. Another factor that will affect your work is the use of a cutting fluid or coolant. The amount of compression required to cut metal produces a lot of heat. At high temperatures, the metal being cut tends to weld itself on the cutting edge of the tool. This effect dulls the tool and leaves a rough surface on the workpiece. The use of cutting fluid is not mandatory, but for most metal, except for brass and cast iron, it is recommended. Cutting fluid cools and lubricates. It prolongs the life of the cutting tools, allows you to cut at faster speeds, and helps to produce parts with a fine finish. As you watch our demonstrations, you'll notice that we're not using a lot of cutting fluid. The reason is because we wanted to get our cameras in close to the action. And to do that, still give you a clear picture, we have to cut back on the fluid. Let's start by looking at the lathe. For most lathe operations, the workpiece is rotated by the lathe spindle, and a cutting tool with a single cutting edge is brought against the workpiece to make the cut. In theory, there are only 3 basic types of cuts in all lathe work. These cuts are turning, facing, and boring. In a turning cut, the tool is moved parallel to the lathe axis to remove material from the outside diameter of the workpiece. In a facing cut, the tool moves at right angles to the lathe axis, removing material on the face or end of a part. A boring cut removes material from the inside diameter of a workpiece. From a practical point of view, that's just the beginning. There are many variations of these 3 basic cuts: drilling, cutting tapers, thread cutting, grinding, and in fact, almost any type of metal cutting operation can be performed on the lathe with the right tools and techniques.
All right, so I just showed you several videos that really specify and talk a little bit about some of those basic machining processes. We talked about milling, we talked about drilling, and we also talked about turning. And in that last video, it did mention also facing and boring processes. Let's keep on going. All right. In one of those videos, you did see, I believe it was a drilling video, that it mentioned speed and feed. Now, there's one more thing I want to add to that, which is the depth of cut. These three parameters are extremely important in any machining process that you're going to be doing, because these three parameters really determine how well you're going to cut your material. And they have to be adjusted depending upon what type of cut you're doing and also what type of material you're cutting. Now, let's look a little bit closer at what we're talking about here. If you're talking about the cutting speed, that's the rate at which a workpiece moves past a tool. So if you think back to the drilling process, the cutting speed will be how fast that cutting tool is spinning. That would be the cutting speed. Okay. Whereas if you looked at turning, the cutting speed will actually be how fast the workpiece is spinning. Okay. In the milling, same thing, how fast the work tool is spinning. Okay. Now, how does the cutting speed influence your machining process? Well, the higher the cutting speed, of course, you can cut more in a short amount of time, but be careful because that also reduces the life of your cutting tool. And so you have to be careful what cutting speed you use, in particular with what material you're using. Typically, for harder materials, you're going to have to reduce your cutting speed so that you won't get a lot of chatter and so that you'll get a cleaner surface, which means that it's going to take you longer to make your cut and to make your part. What about the feed? So the feed rate is the advancement of the cutting tool along the workpiece. And so, for instance, in drilling, how fast is your tool is going to be spinning, but how fast is it actually going into, what's that rate that's actually going into the workpiece? Okay, so that's the feed rate. In the milling process, your feed rate is going to be how fast that part is going to be moving past your spinning tool. Okay, because in milling, it's the workpiece that moves, not the spinning tool typically. Sometimes the tool does move in the milling process. Then you look at the turning process. In the turning process, you have the workpiece spinning, and then you have your work tool. Its feed rate is how fast it goes along that spinning part. Okay, and so this can be measured in distance passed per revolution or per cycle, inches per minute, inches per revolution. Okay, anything like that is going to be your feed rate. So how does your feed rate influence your machining process? Well, I thought this picture right here of a little kid mowing his lawn was a good example of how to explain that. Your feed rate is how fast you push that lawnmower. Your speed is how fast your blades are spinning. And so your blades are spinning at a certain rate, that's your speed. If you push that lawnmower too fast as it goes forward, guess what? You're going to have little pieces of grass sticking out because you're going to miss them. It's going to be very rough. And the same thing is what happens when you increase your feed rate too fast. So faster feeds, they will shorten your work time, so that's pretty good, but they can give you a rougher surface. So again, you have to kind of balance that out. Now, what about depth? So depth is pretty much how deep your work tool goes into the workpiece, how deep the cutting tool goes into the workpiece. And that can be measured just by how thick that chip or the layer removed from the workpiece is. Now, how does the depth influence your machining? Well, that depth of cut is going to, of course, determine the width of the chip. Now, the width of the chip, we're not going to go into that, but there's a whole entire science that studies the chips that are created during the machining process, because the chips that are created are related to how well the machining process takes place. They're related to the heat that's produced there. They're related to the pressure. They're related to all sorts of different things. But of course, we're not going to go that deep into the chip, but just know that that depth of cut can determine the width of each chip that's being removed from the part. Now, what might be some problems you want to look out for? There was one problem in particular that was mentioned in one of the videos that I showed you. I wonder if you can think of any of those problems that we really want to look for when we're doing the machining process. One of those problems is deflection. And to mention this, in particular with the milling process. And so since you're milling and you have your tool, okay, coming straight down, your cutting tool coming straight down, but it's going at the side, pushing at the side a lot. It's cutting at the side. And so there can be some deflection that happens there. Okay. And of course, because of that, that limits the precision of the milling process. Also, you have to be careful of the heat. The guy who was talking about the smithy, which is kind of a do-it-all lathe, was telling you hey, cutting fluid which lubricates and which cools is always good to have typically. And that's because you want to find some way to transfer that heat from where the cutting tool is actually going into your workpiece, because there's a lot of heat that's being produced in that process. All right, now let's look at the quality of your workpiece materials. A lot of people will talk about machinability, and the machinability, I know it sounds like a made-up word, but it really just means that, hey, how easy is it for me to machine this material? So this is usually based on a couple of different factors. So the surface finish and the surface integrity of the machined part. So if you can machine it and have a really good surface finish, and your surface is together, doesn't have a lot of cracks, doesn't have a lot of voids, doesn't have a lot of imperfections, then you're going to have a good machinability for that type of material. It can also be based on the tool life. So if you're cutting a particular material and you're running through these cutting tools like nothing, then your tool life is very, very low. That material has a low machinability because you're going through all those cutting tools so fast. It also focuses on, or also involves force and power requirements. So how much force, how much power do you need to actually cut that material? And then the level of difficulty in chip control. I told you before that having that those chips can be very, very important. Maintaining a consistent size of chip is important because that relates to how consistent your cut is. Now, of course, harder and stronger materials are going to require more cutting forces rather, because they're harder. And so it takes more force to engage and to cut that material. Examples of materials that are harder, that have a low machinability, would be titanium, okay? Because titanium is very hard. Now, ductile materials, of course, will require less forces, and they'll have a higher feed rate. So remember, the harder your material, the lower your feed rate is going to be. Materials, you have to be careful because super ductile is not always good either, because materials that are too ductile, they will develop the BUE. And the guy who was talking about the smithy, kind of mentioned this a little bit before, but BUE stands for built-up edge. And what happens with the built-up edge? Well, what happens there is that your material is so soft that layers of material from your workpiece start to get essentially welded onto your cutting tool. And this affects the geometry of the cutting tool. It dulls it, and it doesn't allow it to have a good surface finish after it's finished cutting. What are some other things you can consider? Well, what about the pressure that the cutting tool has to exert on the workpiece? It's very, very high pressure, which means that you want a very stable setup to withstand everything. Okay. We talked about the heat before, how those forces and pressure create a lot of heat. And one question I would like to kind of ask you is, well, how do you think that heat is dissipated in machining? A lot of people will say, well, you do have the cutting fluid, okay, and you do have that fluid lubricant coolant, and that's good. That lubricant and that coolant is used to help transfer some of that heat from the point at which that heat is being produced, but that's not where most of the heat goes, or that's not how most of the heat goes from that point. You can also think of, well, the heat can be transferred, or it can be moved through the actual workpiece, which can happen as well. So the heat is being caused right at the point where it's being cut. That heat can be dissipated through the rest of the workpiece. That's true. But again, that's not where most of the heat is being dissipated from. Most of the heat is actually being taken care of not by lubrication, though lubrication is involved, as I mentioned before. But I thought I had answered here. But it's taken care of by the chip. So the chip that chips away, that's actually carrying most of the heat, which is another reason why those chips are so important. Now let's take a closer look at cutting tools. What do we consider when we talk about cutting tools? Well, first of all, they have to retain their hardness at high temperatures. That's called hot hardness, because you're going to have high temperatures when you're doing this machining process. And if the cutting tool isn't hard enough, it's not going to be able to shear off that material. It's not going to be able to cut into the material to make your part. Also, you want to think about, well, what cutting speed do we need? So high speed will equal higher productivity, but faster cutting, again, will wear down your cutting tool, okay? And it will increase the heat. A lower speed, of course, your tool lasts longer, but then you have lower productivity. Now here's some of the basic types of cutting tool materials. First of all, you will have high-speed steel. Okay. Now high-speed steel is the most commonly used cutting tool material. You find that in a lot of machine shops, sometimes they even commonly use carbide cutting tools. But high-speed steel is steel specifically made to be able to withstand and to retain its hardness while at high temperatures. Okay, so that's high-speed steel. Then you have carbide cutting tools. So these tools are made of tungsten carbide. This is a completely different material. It's a lot harder, and it has a better hot hardness than high-speed steel, which means that it can retain its hardness at higher temperatures better. Since it can do that, then that means the cutting speeds you can use with carbide cutting tools are 3 to 4 times faster than the cutting speeds you can use with high-speed steel. Now, the next type of cutting tool material, is ceramic cutting tools. Now, these are used to machine very hard workpiece materials because ceramics is very hard in itself. They have a better hot hardness even than your carbide cutting tools and can operate at higher speeds. But the thing is that they require a very rigid setup. Because they're so hard, they're also very brittle. So that means that the setup does not dampen out a lot of vibration, then these cutting tools can break. You don't see ceramic cutting tools a whole bunch. Most of these days, you see a lot of carbide cutting tools and some high-speed steel. Now, the next step up from that is your diamond and cubic boron nitride. So cubic boron nitride is kind of like a laboratory manufactured diamond material. But a lot of times, your diamond and your cubic boron nitride, a lot of times they just coat, so they're diamond tipped cutting tools. Not the whole thing is a diamond, or the whole thing isn't CBN, but diamond is one of the hardest substances on this earth, and so that's why it has such a high hot hardness. So you use it to produce very smooth surfaces or very close tolerances. Of course, your diamond cutting tools are going to be harder. Your CBN tools, cubic boron nitride, are the second hardest as compared to diamond. Now let's watch this video on cutting tools.
The selection of a cutting tool is probably the most important decision a machinist can make. We're going to cover some of the basics, but I urge everyone that intends to use a lathe to learn as much about cutting tools as possible. They're the key to the quality of your work. Lathe tools are made of many different types of materials in many sizes and styles. The 3 types we're using today are, from the left, high-speed steel tools, carbide tip tools, and on the right, carbide insert tools. High-speed steel tools can be used for many turning operations on all but the toughest alloys. The tools are sold as blanks in many sizes and grades. The machinist grinds the point of the tool depending on the type of metal he's cutting and the type of turning operation he intends to do. A good machinist handbook will give you the standard guidelines for grinding high-speed steel tools. The cutting edge of a carbide tip tool is brazed to the end of a steel shank. The shape of the cutting edge, its profile, and cutting angles are manufactured into the tool. A little cleanup on a green wheel, a silicone carbide grinding wheel, and the tool is ready to go. Cemented carbide will handle much more heat than high-speed steel, so carbide tools are able to cut tougher metals and cut at higher speeds. Cemented carbide is also used to make small inserts that are clamped to a tool shank. This style insert is manufactured with a cutting edge on each of its 3 sides. After an edge is dulled, the insert can be unclamped and rotated to the next side. After all the edges have dulled, the insert is thrown away and replaced by a new one. Although this type of cutting tool was designed for the demands of high production work, it's really a great tool for the beginner because it allows even the person with little or no tool sharpening experience the ability to easily maintain a properly formed, sharp tool. No matter what type of material the cutting tool is made of, it's the shape of the tool that determines how it can be used. The profile of the tool's point determines the type of cut the tool is designed to make. The location of the cutting edge on the point of the tool determines the direction in which the tool will cut. Turning and facing tools are either right or left hand tools, depending on which side of the tool's shank the cutting edge is ground. Right hand tools cut from right to left because the cutting edge is on the left side of the tool's point. Facing from the center of a part to the outer edge, cutting right to left, requires a right hand facing tool. Left hand turning and facing tools cut from left to right. Cutting away from the headstock in a turning operation, or from the outer edge to the center in a facing operation. The cutting edges on these tools are on the right side of the tool's point. Sending a tool straight into a workpiece is called a plunge cut. This type of cut requires a tool that has the cutting edge square on the nose of the tool. Here we're using a high-speed steel cut-off blade and holder. The position of the cutting tool in the tool holder is very important. Tools should always be placed as far into the tool holder as possible to give the cutting edge adequate support and to reduce the possibility of the tool vibrating. In the case of a boring tool, only the length needed to clear the hole should extend out beyond the tool holder. The height of the tool should be set to match the center of the lathe axis. A lathe center placed in the tailstock can be used as a gauge to set the height. On this tool holder, shims and spacers are used to raise the tool. The tailstock is also used as a tool holder for drilling, reaming, countersinking, and thread tapping operations on the lathe.
All right, well, if you didn't know anything about turning and if you didn't know anything about cutting tools, well, you definitely do now. Let's continue on. And that is the end of this particular presentation. Thank you very much.